Wow, would you believe it? We made it to the end. This is the last chapter. And since this is the last chapter, and we have been talking about matter since you start taking chemistry 1411, let's go ahead and finish by going deep into matter. So we're gonna go back to the nucleus. So up till now, all the reaction that you have seen, gas laws and all that depends on the electrons, mostly the valence electrons. This chapter is gonna deal with the nucleus. So let's see what happens inside the nucleus in terms of nuclear reactions or nuclear chemistry. To do that, we're gonna understand some of the concepts first. So we're gonna be talking about nuclear decay, basically something that is deteriorating or breaking apart. We are going to learn different terms that we need to use to be able to talk about nuclear reactions. And since we're gonna be doing reactions, but this time nuclear, we're gonna learn how to write balanced nuclear equations to show what's going on, or the transformation or transmutations. And all these nuclear reactions happens because we're gonna see that some of these nucleus are unstable, and they're gonna have to reach stability somehow. So some very few elements are gonna be very stable by nature. Most of them are gonna have to do something. They're gonna have to transmutate to become stable. The stability we are going to see that it's gonna depend on the amount of neutrons and protons, or the ratio between them. And once we do that, we are going to see that we are gonna be able to measure how fast these reactions happens, the same way we used to do kinetics with chemical reactions. We're gonna be doing kinetic with nuclear reactions. And what we're going to see is that all of these nuclear decays are going to be first order reactions, which means all those integrated first law for first order reactions that you learned, we're going to use here. Half-life for first order kinetics are going to be also used here. So you, with this part, you're very familiar. You just have to be able to apply the new terms that relate with nuclear reactions. And we're specifically going to talk about fission and fusion as ways of generating energy by breaking or combining different types of nucleus. And I hopefully are going to be able to close the chapter by showing you something that happens just this last February that is probably going to change your life forever during your lifetime. And your kids are going to be enjoying such a better world if that goes through. And with that, we're going to see how all that applies to the operation of a nuclear plant and what is all the hype about it. So let's begin by taking three objectives at the same time. We're going to define what nuclear decay is, or the process, the terms that we need to understand that, and how to write nuclear equations. So let's begin with a quick review of what you learned back on 1411. On 1411, we talked about isotopes when we were learning the composition of the nucleus with protons, electrons, neutrons, and so on. And you probably saw a symbol like this, where we express the atomic number and the mass number. And you probably remember that back then you learned that the mass number is nothing more than the mass of the protons plus the mass of the neutrons. And the atomic number is nothing more than the number of protons. And given that this particular symbol is neutral, is not a cation, is not an anion, then the number of protons has to be also the same as the number of electrons. So all that you learn on 1411. So, new term, a nucleon. A nucleon is just a particle that is inside the nucleus. Which particles are those? Protons and neutrons. So the protons and neutrons are known as nucleons. By the way, when we talk about the nucleus of the atom, that would be one nucleus. This would be the plural for nucleus. That would be more than one nucleus. You already know that the number of protons is going to equal the atomic number, and that the number of protons and neutrons together is the mass number. So this is a way to write an isotopic symbol, just like you saw here, atomic number at the bottom, and since this particular isotope has 6 neutrons, 6 protons plus 6 neutrons is 12. An isotope of this would be, for example, that. Same element, but now we have 8 neutrons instead of 6 neutrons. That will not be an isotope because it's not the same element. So, just refreshing, isotopes are same elements with different number of neutrons, and we're going to show those with this symbol. However, we can also write isotopes this way. So for example, uranium-234 means uranium mass number 234, and when we look at the periodic table, we know that uranium is atomic number 92. So uranium-235 would be 92, 235, one more neutron, and uranium-238 would be 3 more neutrons than the previous one. So there's 2 ways to write an isotope. You can spell out the name and dash mass number, or you can write it with the symbol and the atomic number and the mass number. And those are what we call isotopes, different numbers of neutrons. And remember, a neutron is a nucleon. A proton is also a nucleon. Would electrons also be nucleons? Not, because electrons are outside the nucleus. So nucleons will be particles that are inside the nucleus, which are only 2, as far as we know today. And we also learned back on 1411 that in nature, they're going to have different percentage of abundance. And when we do the average of those abundance with their weights, that's how we get the atomic weight, which is the weight that shows on the periodic table. So the mass number is very different from the weight that shows on the periodic table. The mass number refers to one atom, how many protons, how many neutrons. The weight on the periodic table is an average of all the different isotopes for a particular element. So now that we have that refresh and back again in your memory, like I told you before, most of the elements are not going to be stable, so they're going to start breaking apart to reach stability. And why is that? Well, let's say, for example, that I have hydrogen. Hydrogen would be 1 proton and 0 neutrons. That's why the mass number of hydrogen is 1, 1. An isotope of hydrogen, and this is about 97% abundance. Most of the hydrogens on this universe is going to be that. An isotope of that is going to be deuterium. And deuterium is like that. And deuterium is going to have 1 proton and 1 neutron. Therefore, mass number 2. And what about another isotope? Another isotope is going to be tritium. So this would be deuterium. And this would be tritium. So those are the most abundant isotope of hydrogens. But, but the hydrogen one is the one that is most of what we find in the universe. So tritium is going to be one proton and two neutrons. So that's not really an example of radioactivity. So what would be an example that lead us to understand radioactivity? Well, let's do something like this. Let's do, like I said before, let's do carbon. Carbon 6. Sorry, carbon is 6, but the isotope is 14, and carbon 6 and 12. So the first one is going to be 6 protons and 6 neutrons. So 1 proton, 2 protons, 3 protons, 4 protons, 5 protons, 6 protons, and we say 1 neutron, 2 neutrons, 3 neutrons, 4, 5, and 6. So that would be that one there. What about the other one? The other one is going to be basically the same thing. So the other one is basically the same thing, but we're going to have 2 more neutrons. Therefore, 8 neutrons on this one. So that would be that one over there. So if you notice, this one, different to hydrogen, have 6 protons. And what do we know about a proton close to another proton? They are gonna repel each other. So as you put more protons to represent the atomic number, there's an immense amount of energy pushing them out. And I showed, and you learn on 1411 that the nucleus is super, super, super dense and concentrated. So all those protons and neutrons, they are super compressed in there. So for nature to be able to keep those protons together, even though they want to repel each other, an immense amount of energy is required. And very simplify the function of the neutron. One of the purposes of the neutron is to prevent them from the nucleus from breaking apart. But there's a point where there are so many protons that nature cannot stabilize it and it start breaking apart. The most classic element that you will think about radioactivity is probably uranium. And when you look at uranium, you have 92 protons. So there's a lot of protons in there. And the mass number is about 235 or 238 or something like that. So you got hundreds, over 100 neutrons in there also. So all those protons trying to stay together is too much. So it starts breaking apart. And when it breaks apart, that's what we call radioactivity. So most of the elements that have a big number of protons, most of them will be radioactive. Most of the elements on the periodic table somehow will be a little bit radioactive. So that's where the radioactivity comes from. The amount of protons on the nucleus is hard to keep them together, and nature decides to break the element apart, releasing protons, neutrons, and stuff like that until it becomes stable. But the problem is, if I have an element with 6 protons, carbon, right? And I lose one of those protons, suddenly it just became boron. So it has transmutated from one element to the other. So radioactivity is going to cause matter to change from one element to another element. So let's see how that happens. So if they are unstable, they can become radioactive. Any nucleus that undergoes this process, we call it therefore a radionuclide. And a nuclide is nothing more than, for example, if I show you something like this, it's just the nucleus with only the protons and the neutrons. And for nature to find that stability, the way it's gonna break or decay meaning that it's breaking apart, there's gonna be several ways to be able to do that. So that's what we're gonna learn. The different type of particles that nature can release to find that stability. And then we're gonna learn how to represent that by writing nuclear equations. So let's learn about the particles that we have to recognize to say, wow, yeah, that's radioactive, it's releasing this or such particle. So here are the particles. It can just decay by tossing out neutrons. So a neutron, like you already know, it's on the table, but I'm gonna have it anyway. A neutron will be an N, right? And a neutron have how many protons? That's a rhetorical question. A neutron have no protons because it's a neutron, right? So 0 protons. But the mass of the neutrons, like the mass of any element, is protons plus neutrons. So one neutron have only one neutron. So that's how you represent a neutron. 0 protons, because it's a neutron, and a total mass of 1 unit. What about the proton? Well, the proton is going to be, we're going to represent that with a P, and 1 proton is 1 proton. No argument there, right? And the total mass of 1 proton is 1 proton. So that would be your proton. The electron is a little bit more interesting. The electrons, for us to be able to keep track of this system, we're going to change it a little bit. So the electron, we know the electron have no mass. So it have no, in terms of mass number, the electron don't have protons or neutrons, right? So that's going to be 0. But for us to keep track of this, at the bottom, we're not putting the number of protons like we did before. We put in just the charge. So on the electron, we put in the charge. That would allow us to keep us track of what's happening when we're doing the nuclear reactions. And then we have something that is a lot more interesting than that, which is not an electron, but a positron. So a positron is an electron with a positive charge. So this can get weird because now we're kind of dipping our toes into physics. Particle physics. We're not going to talk about that, but we start relating this with the quarks ups, quark downs, muons, and all those particles that you hear on science fiction movies and so on. Because the neutron, protons, and electrons, for a chemist, that's as far as we can go. For a physicist, they can take that neutron and break it into those elementary particles, and they can keep going deeper and deeper into matter. For the purpose of the chemist, neutrons, protons, and electrons, that's good enough. That's as far as we're going to go. So all those particles that I just mentioned about, they can combine different ways to take a neutron and make it into a proton. So you're going to see that when we do the chemical reactions, the nuclear reactions. And then the other particle we have is so we got that. Notice this here. So an electron, when it's part of a nuclear decay, we call it a beta particle. And it can be expressed with this symbol here. So consider an electron and a beta particle the same for our purpose. So the only one we have remaining is an alpha particle. And an alpha particle is nothing more than helium, two protons, two nucleus. Two protons is going to have two electrons, right? So that would be helium, but we're not talking about helium. We're talking about the nucleus of helium. So we're going to take out the electrons, which means this just became 2 plus. So an alpha particle is nothing more than a helium nucleus without the electrons. For the purpose of nuclear chemistry, nuclear reaction, we don't put the 2 plus in there. We just know that if we're using this symbol, we are only referring to the nucleus. We don't care about the electrons. So an element can break into that big chunk, 2 protons and 2 nucleus, to find stability. So it's super important that you either memorize how to write each one of these particles, know their names, or have it on your notes in a place where you can find them really easy and understand what they are. So how do we relate this to radioactive decay? Well, if we talk about alpha decay, that means that something releases an alpha particle. If we're talking about beta decay, that means that something is releasing a beta particle. Or you can also write like this, a beta particle. The positron, that means that something just produce or emit or decay via a positron emission. You can also write a symbol like that. That means a positron. An electron capture, you can also have neutron capture. That means that something gain an electron to produce something. So you gotta be looking for those words. Captures mean that it's gonna be a reactant. Absorption means it's gonna be a reactant. Decay or emission means that it's a product. And then you just have to put whatever we have in there. There's one that I haven't done, which is gonna be gamma emission. That means that something releases gamma emission, and we're gonna represent gamma with the gamma symbol from Greek. And this is pure energy, so there's no protons, there is no mass. It's just energy. So what happens is sometimes an element is very unstable. It releases an alpha particle or something like that, and after releasing that, it's still unstable. And that means that it still has too much energy, so it just releases the energy by itself to reach final stability. So this is pure energy. So that's what decay means, or emission, or capture, or absorption. So make sure that you're looking for those words and kind of figure out, once we start writing nuclear reactions, where you should put those particles. So remember, have those particles handy. So a table like this, you should have it handy at all times, or even better, memorize it, which you're gonna do anyway with practice, which is the best way to memorize, by working the problems. So like you already know, if you're doing a regular chemical reactions, the atoms and the charges have to balance. You cannot violate the law of conservation of mass. So when we do nuclear reactions, the atomic number and the mass number have to balance. So let's do an example. Let's do these three reactions. So the first one is decay. So it's gonna produce, what is it gonna produce? Decay of nitrogen. So nitrogen, we know that nitrogen is atomic number 7, and we're talking specifically about nitrogen 13. So write it like that. Decay of nitrogen 13 via positron emission. So this is gonna emit a positron, which is a plus 1, 0. And this size has to balance with this side. So on this, the bottom number is a 7. On the other side, the bottom number is a 1. So I'm gonna have to add something. I'm gonna put something there with a 6 to make it 7. On top, I have a 13, and this is gonna be a 13 then. So top number on the left side, 13. Top number on the right side, altogether, 13. Bottom number on the left side, 7. Bottom number on the right side, all combined, 7. Now that I know this is atomic number 6, I can say, oh, atomic number 6, that's gotta be carbon. And then you put the symbol. And that will be when we have nitrogen 13 that is unstable, it becomes stable by transmutating into carbon 13, but to do that, it has to release a positron. So it's decaying by a positron emission. Let's do the next one. So on the next one, we're gonna have another decay. So it's gonna be producing a beta emission. So beta is just like an electron, -1 and 0. And what is decaying? Lead. Lead is decaying, and it's lead 214. So lead 214, and lead is atomic number. Let's see. I cannot see it from here. Let me pull out my periodic table. Just a second. And if you thought I had all these elements memorized, you were wrong. 82. Most of them I do, but not all of them. So this is atomic number 82. So lead 214 is decaying, so it's producing a beta particle. So on the left side, the bottom number is 82. So on the right side, it would have to be 83, because 82 minus 1 is 82. On the left, on the bottom, the top number is 214 on the left, and I'm gonna have to put 214 to make it 214 on the left. And that means that atomic number 83 is gonna be bismuth. So what this is saying is, for lead 214 to become stable, it's gonna have to let a beta particle come out, which is gonna change this nuclide from lead 82 to bismuth 83. So matter cannot be created, matter cannot be destroyed, but matter can be transformed, which is what you're seeing in here right now. Lead is being transformed into bismuth. And let's do the last one. The last one said neutron induced. So this is going to happen because we are adding a neutron. So we're going to have a neutron, which is 0 and 1. So we are inducing fission, which is breaking apart. And what are we breaking apart? Uranium-235. So uranium which is number 92, and a mass number of 235 because it's telling me so. And it's gonna form, so it's gonna produce xenon 144, and xenon is going to be number 54, atomic number 54, and strontium 90. And strontium is going to be 38. So this one is a little bit more challenging than the other two. So write a nuclear reaction for the neutron-induced fission. So it's fission because one element is becoming two elements, so it's breaking apart into two, splitting, to form that, and how many neutrons are produced. So it's telling me that I'm gonna produce neutrons, but it wants to know how many. Okay? So let's see. On the left side, the bottom number is 92. On the right side, the bottom number is 92. So the bottom number is good. It's balanced. It's 92. It doesn't matter how many neutrons I put in there. It's times 0, so that's not going to change. On the top part, the top number is going to be 236. And the right side, we're going to have so far 4, 13, 234. So that means that I'm going to need 2 more to balance. And if I'm using neutrons, that means I'm going to need 2 of them. So that's what we're going to have here. We're going to have, let me give myself some space. We're going to have 2 neutrons. And that will balance this equation. So let's double check. So on the left side, the atomic number altogether is 92. On the right side, the atomic number altogether is 92. On the left side, the mass number, the number on top, is 236. On the right side is also 236. So this shows us an element splitting. So one element is splitting into 2. So that's what we're going to call fission because it's being split. And we use 1 neutron to split it, but in the process, it produced 2 neutrons. So imagine if we have millions and millions and millions of atoms of uranium-235, and every time I use a neutron, 2 neutrons are produced, and each one of those neutrons attacks a uranium-235, and each one of them produces 2 more. So that's what we're going to call a chain reaction. A chain reaction is when one fission incident produces exponentially a bunch of the same processes, which is how a nuclear bomb works. So with that said, let's see if you can work on this daily work. And once you do that, we're going to say that we're done with this objective. So now you know what a nuclear decay process is, and you know the particles that can be involved with that. We talk about nuclide, nucleons, decay, absorption, all the different particles, fission, transmutation. So we define a lot of terms associated with nuclear reactions. So make sure you review those. And you see the basic of writing nuclear equations. which is very easy. You just have to be able to add and subtract using the periodic table to keep track of your atomic numbers and your mass numbers, and using the new particles that you just learned. So when we come back, we are gonna begin talking about stability. How do we know that an element most likely will decay? How do we know that an element probably is stable the way it is and we shouldn't expect any radioactivity from it? So that's what we do when we come back. So we'll see you soon. Take care.